I'd like to do a few examples of related rate problems. In related rate problems, we have variables that are tied together in some sort of relationship, an equation, and at least one of the variables is changing, and that change in that variable to maintain the relationship, to maintain the equation being true, induces changes in the other equation, the other variable. Now, if we know how fast one or more of the variables is changing, what we'd like to be able to do is from that determine how fast that the other variables are changing. So let's take a look at an example of this, and I tried to start off with a fairly simple example. This example is we have the point xy is moving along the graph of y equals x squared. And at one point in time, x is equal to 4, and it's decreasing at 0.3 units per minute. What is the rate of change in the distance from the origin to that point? Let's take a look at a picture of this. Here we have the graph of x squared, okay? And we have a point on that curve. And what's happening as time goes by, the point is moving closer, the x-vat coordinate is decreasing, so we're moving to the left. And notice the distance to the origin is changing. If at this time when x is equal to 4, okay, when x is equal to 4, if the value of x is decreasing at 3 units per minute, how fast is this distance to the origin changing? That's what we'd like to determine. So let's take a look at, and this is sort of the routine that I would kind of use to set this up. We have the values involved are basically d, all right, the distance to the origin, and that distance to the origin, I would want to write an equation that relates it to the other variables, is the square root of x squared plus y squared. That's how far a point xy, that's how far a point xy is from the origin. So there's a relationship between those. Further, we know that y is, since we're on the parabola, y is given by x squared, so I can replace the y with x squared, and I'll have d is equal to, I'm going to write it this way, x squared plus x squared squared is x to the 4th, all right, to the 1/2 power. And I'll write it that way because that will facilitate a derivative. So I have these two variables. I have x, and I know the value x is equal to 4, and then its rate of change is going to be the derivative of x with respect to t. Okay, notice that it's x in units per minute, so units are x changes in x, and minutes are changes in time. And this is negative 0.3 units per minute. D, I don't know the value of it. I may not need to know the value of it because d may disappear when I take a derivative. So that's one thing that I'll not worry about evaluating this unless I absolutely have to. And then the rate of change in d with respect to time is what we're looking for. How fast is d changing? So I'll signify that by a question mark here. Okay, so now let's take this, and what we're going to do is we want to find the rate of change in d with respect to t. So I'm going to take a derivative of both sides of this with respect to t. So the derivative of d with respect to t is equal to the derivative with respect to t of x squared plus x to the 4th raised to the 1/2 power. The derivative of d with respect to t is just dd dt, and that is equal to, well, now let's see, I have to use a chain rule here, so the outside function is the square root, or raising to the 1/2, so I'll use the power rule to take the derivative of that. I'll have 1/2 x squared plus x to the 4th to the negative 1/2, then times the derivative of what's inside. Now you have to be a little bit careful here because what's inside now is still a composite function. We have this function evaluated at x squared plus x to the 4th evaluated at x, but x in turn is a function of time, is changing with respect to time. So I have the derivative of this all right, which would be 2x plus 4x to the third, all right, times the derivative of the inside function for this function, which is just the derivative of x, and that would be dx dt. All right, now I know all these values. I know, let's see, I know that I'm going to evaluate this thing, and I'll just write these down at x is equal to 4, and dx dt is equal to negative 0.3. And so if I evaluate that, I'm going to get 1/2. 1/2, all right, well, x is 4, so 4 squared is 16, plus 4 to the 4th is 256, raised to the negative 1/2 power, excuse me, times 2 times x, which is 4, is 8, times x to the third, 4 to the third is 64, times 4 is 256, all times dx dt, which is negative 0.3. And now if I evaluate that, that turns out to be a negative, or well, approximately, it turns out to be an irrational number, but it turns out to be approximately negative 2.4011. And I just had this down here to remind me of that. So d is decreasing at that point in time. D is decreasing at 2.4, almost 2.5 units per minute. That's the rate at which d is getting smaller. What I've done is I've developed a spreadsheet, but in the spreadsheet I've made a mistake. This should be in t in minutes. And notice what I started out. I started out with a time negative 1/2 of a minute, and then negative 0.45 minutes. So that's gone down by 5/100ths of a minute, or time is increased by 5/100ths of a minute, and then again 5/100ths, and so on. And x is decreasing along with the increases in time. You can see that x is going down, and it's going down at a rate of 0.3 units per minute. So that if I go from negative 0.5 to positive 0.5, this has gone down by 0.3 units, so from 4.15 down to 3.85. All right, and it's done in equal increments. And what I've done is I've looked at this at our time 0, we're at 4. I've adjusted the formula so that would happen. That's where we're interested in this. And notice if we look at the time immediately before at negative 0.05 minutes, and time immediately after, all right, at least in this table, 0.05 minutes. All right, the distances, the x values are 4.015 and 3.985, and the values of y I've calculated, and the values of x squared plus y squared, which would be d squared, I've calculated, and here are the corresponding values of d. If I take the difference in the d values, I get the change in d is this negative 0.24, and if I divide that by the change in time, which is going to be 0.1, when I divide by that, I get this negative 2.401, the very same thing that I got this way. This won't always give me an exact value, and it's not really an exact value. If I would display enough digits, we'd see them differently, because this is an average rate of change, and that just estimates an instantaneous rate of change, a rate of change at one point. But anyway, I just wanted to show you that table because it's further evidence that what we've done makes sense. It actually works. So here's the example of one related rate problem. In upcoming videos, you'll see the other ones. So see more examples, I should say. Okay.